I want to just start off with this idea of what we're going to do here. So I'd like to add together 1/2 plus 2/3. All right, so if I was going to add these two fractions together, the problem that we first face here is that they're different sizes of pieces, right? The denominators are different. And because the denominators are different, I can't add them. So if I'm going to add them, I would have to make sure that their denominators are the same. So I would have to multiply the left one by 3/3, and I'd multiply the right one by 2/2. So basically, I was just multiplying by what was missing from the other piece. So if this one has a 2 and this one has a 3, then that means that this one needs a 3 and this one needs a 2. Which is why this here just becomes 3/6 plus 4/6. And my answer is 7/6. Easy enough? Hopefully. Well, notice now that I asked you a different question, okay? What if I now ask you, what two fractions added to get 7/6? Now you might cheat because we just did this problem and say, oh, obviously 1/2 plus 2/3. The problem is we don't know for sure that that's actually what they are before we did the problem. So if I'm trying to figure out, okay, well, I know that two fractions added together to give 7/6, but I can't figure out what they are. I first of all have to think, well, they obviously would have to have denominators of 2 and 3. So if they were going to add together, I couldn't add fourths and fifths to somehow get 6, right? The only way to add numbers together to get 6 is to realize that 6 is 2 times 3. So that would mean that if I was going to break this apart, then I would have to realize that 7/6 can be written as something, I don't know, let's call it A over 2, plus something else over here, B over 3. So what we can see here is that we are trying to decompose the fraction 7/6 by breaking it up into its smaller pieces. All right? Now that's all I'm going to do on this one for a minute here. I'd like to now go ahead and take a look at an example as to why this is important. So let's say that this right here was the integral that we're trying to integrate. It's a rational function, right? A polynomial over a polynomial. So I've only got a couple of options here about how I might solve this. One method is to use U-Substitution, maybe. The problem with that is that the U-Substitution doesn't look like it would work on this problem, okay? I encourage you to try it and see why. So instead, there has to be some easier way to do this. But I don't know how to integrate functions where the denominator doesn't have a numerator that's its own derivative. So that's why if you looked at the lecture notes, I'm just going to kind of go through these lecture notes real quick. I'd like to just recap a couple of rational functions that we are able to integrate. Okay, so taking a look at this one right here. Okay. We can integrate this pretty easily because the derivative of the denominator is 6x squared. So since I see a 6 there already, or since I see an x squared here on top, then I'm just going to multiply by 6, pull out a 1/6, and now I could see that the derivative, the integral, is just going to be the natural log of the denominator. But this was just a special case because the numerator just happened to be the derivative of the denominator. That's not always going to happen. So what if we were to now look at this next one here? Okay. Well, if I wanted to take the integral of each of these pieces separately, I could realize that the integral of 2 over x minus 1 is just 2 times the natural log of the denominator. Because if this denominator is linear, then the derivative of x minus 1 is 1. And so I should be able to just take the integral of this function on the left here as being 2 ln at the bottom. And of course, this one over here is just minus 1 ln at the bottom. Well, now what I'd like you to do is take a look at this real quick. See how these two fractions are now subtracted? That's the same exact integral that I asked you to find right here, right? So what if I were to subtract these two quantities right here by getting a common denominator? Then this one over on the left would need an x minus 2. This one on the right would need an x minus 1. So I merged them into 1. And when I simplify, this right here is the new function that I get. Right? So what you should agree is that if I were to integrate this function, can anybody tell me what the answer would be? What would the integral of this function be? I'll give you a clue. We already know it. Can somebody tell me what the integral of this is?
2 ln of absolute value x minus 1 minus ln of absolute value x minus 2.
Very good. It's this. The integral of this function down here is 2 ln of x minus 1 minus ln of x minus 2, because these two functions are exactly the same. This function is the same as this function, so they should have the same integral. The problem is that if it looks like this form right here, then we could integrate it easily. But if it looks like this form, then we can't integrate it as easily. So any idea on what our goal is going to be here?
Make our complicated one looks easier to integrate.
Exactly. Our goal is to somehow make our complicated function look easier. And that's why we're going to go back to this example. And we're going to try to find out the way that we're going to be able to rewrite this as the integral of 2 over x minus 1 minus 1 over x minus 2 dx. If I could rewrite it in this form, then it would look a lot easier. Or it would integrate a lot easier, I should say. All right, well, the problem is, how do we do that? So this is where we first of all need to factor the denominator of this integrand. So we're first of all going to recognize that this could be rewritten as x minus 3 over x minus 1 times x minus 2. Okay. Now, because I see these two distinct linear factors in the bottom, okay, then that must mean that this came from adding together two different fractions, one of which had a denominator of x minus 1, one of which had a denominator of x minus 2. The problem is, I don't know what the numerators were. Okay. Now, first of all, you should recognize, see if the numerator is a lower degree way over here. If the numerator is a lower degree than the denominator, as it should be, then that must mean that each of the fractions had a degree lower than the denominator as well. So if this denominator has x minus 1, then I know that the numerator is going to have to just be some constant. And if the denominator of the second fraction is x minus 2, then I know that this denominator has to have a b. Everybody okay there? All right, and our goal is to figure out what a and b are. Now, again, if we cheat a little bit here, we know that what a and b actually are, right? We know that a and b are going to be 2 and negative 1. Because we kind of already looked at this problem in the reverse direction, okay? Right now, though, unfortunately, we don't know that. So the key we're going to do here is we're going to get rid of these fractions by multiplying both sides by the common denominator. So if I multiply the left over here by x minus 1 times x minus 2, and I multiply over here as well by the denominators of x minus 1 and x minus 2, then what I should be left with is just x minus 3 on the left side. And on the right side, we're left with a times x minus 2 plus b times x minus 1. Okay, so we just canceled out the common denominators and wrote what was left. And if we expand this a little bit more, we get x minus 3 is equal to ax minus 2a. And then for the second one, we get bx minus b. Now let's not forget about the fact that what we're trying to do here is find out what a and b are, right? So we're just doing some algebra to figure out what a and b represent. Now I'd like you to take a look on the left side over here and realize that we have an x term and we have a constant term. Okay. Over here, I have an x term, but wait, here's another x term. And then I also see a couple of constant terms over here. So I should realize that if these two are apparently equal, as it's supposed to be, these two sides are supposedly equal, then that must mean that the x coefficients on the left should match the x coefficients on the right, and the numeric or the constant coefficients on the left should match the constant coefficients on the right. So before jumping to conclusions here, I'm going to make one more step here, and I'm going to write this as 1x minus 3. And on the right side, I'm going to clump together these x's to get a plus bx plus negative 2a minus b. Hopefully you can kind of see where we're getting at now, because now that must mean that 1 is the same as a plus b. And it must also mean that negative 3 is the same as negative 2a minus b. So that must mean that we can now just solve this system of equations, which is a plus b equals 1, and negative 2a minus b is equal to negative 3. So look through that process that we just did in order to find out what the, what the separate numerators were going to be. And hopefully you could recognize what our purpose is. I can integrate any function over x minus 1 or x minus 2 really easily just by using a natural log function. So this is the process we're using in order to find what a and b actually are. Well, now we just do a little algebra. If I add together our b's, I end up getting that negative a is equal to negative 2, which implies that a equals 2. Okay, well, that's nice. If a is equal to 2, I could plug that in and find out what b is. So let's go ahead and do that. That means that 2 plus b is equal to 1. So subtract 2, and we get that b is equal to negative 1. And now we've got to go back to the original problem and realize what the whole point of this was. Notice that what we've done here is we've just determined what a and b are, which not surprisingly turn out to be the exact same things that we knew it was going to be at the beginning. Right? So notice that what we can do at this point, the whole point of finding a and b, is so that we can now rewrite this integral. So we could say that the integral of x minus 3 over x squared minus minus 3x plus 2 dx. We don't know how to integrate that right now, but what we do know this is equal to is the integral of a, or 2, over x minus 1 plus negative 1 over x minus 2 dx. Last step, notice that this is a nice simple integral. It's just 2 times the natural log of the bottom, 2 ln of the absolute value of the bottom. And then over here, this just becomes minus 1 times the natural log of the absolute value of x minus 2. Cool. Plus c. So any questions on there? So this is a brand new method then of being able to decompose. We call that partial fraction decomposition, because what we've done is we've started with a single fraction and decomposed it into its partial fractions. Everybody cool with that? Any questions? Right on. All right, well, this is one situation that can happen. I just kind of want to scroll through again these notes just to show you a little bit more. It says if the degree is less than the top, if the degree of the top is less than the degree of the bottom, then we know that we could just separate it like this. The problem is, what if we notice that the degree of the numerator is greater than the degree of the denominator? Then we can't actually do this process until we force this to become a different form. So this is where we have to go back to algebra and do long division or synthetic division. Okay, so I'm not going to go through this whole process here, but you can technically see what's going on here. I'll just have you take a look for a second here on your own at the just at the different work here. If you take a look at this work. If you take a look at this work right here on how to do long division of the polynomials again, or if you chose to, you could have done synthetic division as well. So I'll just have you take a look at that for a minute on your. Okay, so you can see what we ended up doing then. So when we had this rational function, since the numerator was greater than the denominator, we ended up dividing, and look at how dividing ended up giving us a different form. So now when we have this different form, notice that all we're expected to integrate at this point is way over here. And by dividing, we ended up getting a polynomial, which is nice and easy to integrate. And then we got a function that's going to yield a logarithm. So anytime the numerator is greater than the denominator, you have to divide. There's no other way to integrate those functions. Pretty all right with that?
So,
okay. Yeah, go ahead.
So with those long divisions, we don't use any A's, any B's, right?
No, it turns out that you don't need to. So whenever the numerator is a higher degree than the denominator, then there's the A's and B's won't work, because notice that the only purpose of finding the A's and B's is that those constants are going to be lower than whatever the degree of the denominator is. But you can see up top that if the denominator only has an x minus 1, just a single linear factor, then I'm not going to be able to break this apart into constants over x minus 1 if the numerator has a cubic function. So instead, we do the long division, like we see right down here, or the synthetic division if the denominator is linear, and turn it into a form that's integrable, which is right over on the right side over here. Okay, so yeah, it's a good point, good question. There is no A's and B's if you're doing it in this method. I'm going to go back up here again, and I'm going to do another little example. Okay, so Let's do another one here. So let's say that we had, what if we had 2/3 plus 1/9? Okay. So now let's think about how to add these two together. So you can see now that, again, these are different denominators of 3 and 9. But I don't need to multiply over here by 9 over 9. It's kind of a waste of time, because notice that 9 already has a factor of 3, right? So what we really only have to do is multiply one of these by 3 over 3, so that now this becomes 6/9 plus 1/9, which is 7/9. Right? So notice that we combined those to get a single fraction here. And so this is our answer. But the question again that is going to have to be asked is, what two fractions add to give 1/9? Now, hopefully you recognize that this was a slightly different process here, because if you look here, notice that up top, 6 had two different distinct factors of 2 and 3, right? But notice that now I'm trying to find out what two fractions add to get 7/9. We should see at this point that 9 has two repeated factors. So this is a slightly different issue, because if I was to try to find out what two fractions to add together by using the previous method, then wouldn't that mean that I would say, well, 7/9 would equal A over 3 plus B over 3. Somebody tell me what the problem with that is?
You would just get 7/9. Oh, no,
But
never
how
mind.
would I get 7/9 if both of these had a denominator of 3? If they
A,
were
B.
already denominators of 3, wouldn't that
You
mean
wouldn't
that
have a whole number in the numerators.
okay, that's true. I may not have whole numbers in the numerators. Secondly, wouldn't that mean that I would never be able to get a 9th on the bottom? Because if I already have two denominators of 3, then by adding them together, I should get a denominator of 3, not 9. So the only way that we could actually do this is that if you ever see repeated factors in the denominator, I can't just write it as A over the first factor plus B over the second factor. I've got to write it as A over the first factor plus B over the square of the second factor. And if there was a third one, then I'd have to write it as C over the cube of the third factor, okay? Or the repeated factor. So the point of this is to recognize that if you ever see repeated linear factors, you have to account for that same factor only being squared. So let's go ahead and now take a look at an example of this. All right, so let's integrate 2x over I'm sorry, I really want a different one. I'm trying to find a better one than this. Oh well. 2x over x plus 2 quantity squared dx. Okay. All right, so we want to integrate this function. Now, again, you may think, let's go ahead and maybe do U-Substitution. And it's very possible that you can definitely do other methods. So if I were to try U-substitution and make this x plus 2, then du is equal to dx. And then it tells me that x is equal to u minus 2. So there might be a way for us to do this using U-substitution. So don't just think that automatically when you see this type of form that you should be doing partial fraction decomposition. Just like if you see a form that says x squared plus 4, you shouldn't just automatically start thinking at this point trig substitution. Remember, U-substitution is oftentimes a much easier process, so I would try that first. So I'm going to try it. Let's just plug in 2 times x, which is u minus 2, so 2u minus 4, over u squared du. And sure enough, if I integrate this, that becomes 2 over u minus 4 over u squared and you should recognize that both of those are integrable. So we didn't need to do this partial fraction decomposition. We're going to do it anyway because that's what we're learning. But I'm just trying to demonstrate to you that I could separate this and just rewrite this as 2 times the natural log of, or 2 times 1 over u du minus 4 times the integral of u to the negative 2 du. And this becomes 2 ln of the absolute value of u minus, and then if I add 1, this becomes plus 4 over u, 4u to the negative 1. Substituting back in, and I get my final answer, which is 2 times the natural log of the absolute value of x plus 2 plus 4 over x plus 2 plus c. So that's our answer, right? So we didn't need any of the method that we're learning today in order to solve this problem, okay? However, U-substitution will not always be possible. And that's why we're going to do this problem again, only we're going to do it in a much different way. So if I were to take this problem right here, I have the integral of 2x over x plus 2 quantity squared. And we're going to see that sometimes I like this method actually that we're about to do. Okay. The first thing we're going to do is we're going to recognize that if we're going to do this partial fraction decomposition, we should be able to rewrite this integrand separately. Notice that we're just doing some side work here. I should be able to rewrite this integrand as a sum of 2 different fractions. So how would I add fractions together to somehow get x plus 2 quantity squared in the denominator?
You could have a over x plus 2 plus b
Yeah, so
over x
one
plus 2
second.
squared.
Good. So first of all, I would have an x plus 2 as one potential denominator for this fraction. I could potentially, though, have an x plus 2 quantity squared for my denominator as well. So if I was going to do this problem, then this is one method I can do, okay? Not one method. So if I was going to do this problem, what I'm saying is that if there's 2 repeated factors, I need to write out 2 separate fractions, one of them with the squared fraction, or one of them with the squared factor, and one of them with the single factor. And now I would say that a over x plus 2 or b over x plus 2 quantity squared. So we're going to do that the same thing as we did in this last example, and let's get rid of the denominators. So let's just multiply by what we're going to need to cancel these. So I'm going to multiply by x plus 2 quantity squared. And on the left one, I'm going to multiply again by x plus 2 quantity squared. Cool. All right, so that gives us that 2x is all that's left on the left side, should equal, and now notice that if I have a single x plus 2 and I'm multiplying by x plus 2 quantity squared, then that must mean that I'm left with a times an extra x plus 2. While over here, all I'm left with is b. So again, just doing a little algebra, let's extend this a little bit. And this gives us that the right side is going to become ax plus 2a plus b. So I'd like you to realize first that a is the coefficient of x. And I'd like you to realize that 2a plus b is the constant. Okay. Well, if that's the case, then that should mean that I should have an x term on the left and also a constant term. But since there is no constant, that must mean that it's nothing, it's 0. Which now allows us to realize that the coefficient of x on the left should match the coefficient of x on the right, and the coefficient or the constant on the left should match the constant on the right. So we pretty much have the rest of our answer, right? We already know based off of equating those coefficients that a is equal to 2. A plus b is equal to 0. Okay, which gives me 2 times 2 plus b is equal to 0. So b is equal to -4. So we found the appropriate a and b values that are going to allow us to separate this fraction and hopefully make our lives a little easier. So notice that this right up here is the decomposition of my original integral. So we're going to rewrite that then as the integral of 2 over x plus 2. And I like to rewrite this as just 2 separate integrals, okay, plus the integral of -4 over x plus 2 quantity squared. And by the time you decompose the fraction, you should be able to integrate each separate piece. You should realize that the left side right here is going to be a natural log function. And because you have a quantity being squared on the bottom, this won't be a natural log function anymore. Instead, you would end up saying that this would be a U-substitution issue, okay? So if you need to do the work there, we can have 2 times the integral of 1 over x plus 2 dx. Let's pull out that -4 times the integral of x plus 2 to the x plus 2 to the -2 dx. And now they're both in a form where we can integrate pretty easily. We can see that the left side is going to be just 2 times the natural log of the bottom. The next one is going to be -4 times. And notice if I add 1 to get -1 and multiply by the new reciprocal, I end up getting plus 4 times x plus 2 to the -1. And sure enough, if you simplify that, then this right here becomes 4 over x plus 2. And you should notice that it's the same thing we ended up getting by U-substitution. So it's a longer process, but sometimes you're not even able to use U-substitution. So this is why you need to be able to do this decomposition to turn each separate integral into a form that is, well, integrable. All right, so we've touched on how to integrate rational functions in 3 different forms. First of all, if the numerator has a higher degree than the denominator. then what do we do first?
Long division or synthetic division?
Long division or synthetic division. Very good. Okay. If the numerator has a lower degree, then what do we do?
Partial fraction decomposition.
Yeah, by factoring the denominators, right? So we want to factor the denominators and then start splitting everything apart. Well, now we've got one last situation here. Okay. And so we're going to do one last example before we finish up here. We are going to integrate 2x minus 3 divided by x cubed plus x. So what we should have noticed when we were, once we factored this problem, okay, you should realize that when you factored, you were only able in this case to factor out an x, and you got this quadratic that didn't seem to be factorable anymore. We actually have a name for this type of factor. It's called a irreducible quadratic. Sometimes we can't break this up into linear factors anymore. So when we have an irreducible quadratic, we realize, well, I can't factor this further, so I know that one denominator is just going to be x, and the other denominator will have to be x squared plus 1. Everybody cool with that? Okay, but now what we should recognize is, since this right here is x to the power of 1, this first linear factor here, I know that the numerator would have to be a degree less. So I would know that this would have to be a, meaning a constant, over x. But over here, now I should realize that this has the highest power of 2. Which means that it would still be a simplified fraction if this didn't just have a constant, like 3, but maybe if it had some linear expression on top. That would still be a simplified fraction right here. And so notice that whenever you see an irreducible quadratic, the tip there, the thing that you need to now take care of is that you might have an x term, and you also might have a constant term. So now you can't just put b over x squared plus 1 anymore. You have to account for the fact that there might have been a linear term and there might have been a constant term. Everybody cool with that? We're going to do the same exact thing we did before. We want to get rid of the fractions to make this a little bit easier. So let's multiply the left side by x times x squared plus 1. And we'll multiply the right side by x times x squared plus 1. Okay, which means that all that's left here on the left is 2x minus 3. While the right side, the x cancels with the x, so we're left with a times x squared plus 1. Plus, and then for this second one, the x squared plus 1 cancels, leaving me with bx plus c times x. So don't forget that the whole point of this again is to get right my a, b, and c values. So we just need to start expanding everything. So we get 2x minus 3 equals ax squared plus a plus bx squared plus cx. And now let's just clump together all of our terms here and realize that we've got a couple of x squared terms. We've got an x term, and we've got a constant term. So if I were to rewrite this then this becomes a plus b is going to be the coefficient of x squared I see that C will be the coefficient of X. And I see that A will be the constant. But if we look over on the right side, notice there is no x squared term. So I'm going to force there to be one by just showing that there's 0 x squareds. And now notice that in equating the coefficients, we can figure out what our A, B, and C are. Okay. So we could see that A is equal to, or A plus B is equal to 0. I can see that 2 is equal to C. And I can see that -3 is equal to A. Cool. So let's go ahead and write these out and just see what that implies here. So that implies that A plus B is equal to 0, so we don't have enough yet to go on that. But what's nice about the other ones is we already know that C is equal to 2. And we also know that A is equal to -3. So if we already know both of those, and I know that A plus B is equal to 0, then that must mean from this one right here that -3 plus B is equal to 0, which means that B is equal to 3. And there's our values. So with partial fraction decomposition, this is just a bunch of algebra again, just to expand to find out what those values of A, B, and C are going to be, so that when I now go back up here, I'm just going to plug in my appropriate A, B, and C values. And at that point, we're going to hope that we can actually integrate. Okay. So let's do that. Let's say the integral of A over X, so that's just -3 over X dx, plus the integral of Bx plus C is just going to be 3x plus 2 over, what was it? X squared plus 1? X squared plus 1. So you might think, well, shouldn't I decompose this more? Well, you can't, because this is irreducible. So I can't simplify this denominator, or I can't simplify this x squared plus 1 denominator any further. So now I'm forced to just go ahead and do other methods that we know in order to integrate these two functions. So anytime you see an irreducible quadratic, you have to break it up into two separate fractions, one in which has the x alone in the numerator, and one that has a constant in the numerator. Okay, because there are some times with irreducible quadratics, like let's just say the numerator, I don't know. I mean, sometimes it'll perfectly work out to where the numerator is the derivative of the denominator, and then U-substitution works, but it doesn't here. So just always make sure that you're splitting it up into this fraction and this fraction separately. Okay. All right. Well, the first and last fractions hopefully were very simple for you. Okay, because this is just the natural log function over here, the integral of 1 over x. And this over here is just our tan inverse function, tan inverse of x. All right. But then we have to do a little bit of work to end up getting this in the right form. So what do we do in order to integrate this function here in the middle?
You could do trig substitution with tangent theta.
Yeah, you could do trig substitution with tan theta. You very well could. Or not. Just do pattern recognition. So but the point of this is that even though we saw that there was an x squared plus 1, I would not automatically default to trig substitution unless you realize that I'm not going to be able to use U-substitution. So what we should definitely do is a little U-substitution, recognize that if the derivative, if I set the denominator equal to U, the derivative of x squared plus 1 is 2x dx. So I can now make the top 2x by factoring out a 1/2. Okay, so just to clarify for those that are not familiar with this pattern recognition idea, all we did here was that we said that all of this is now going to be u, while all of this up top is du. And so all that's left is 3/2 times the natural log of the bottom. Now notice that I could actually just put this in parentheses. I don't need the absolute value because I know that x squared plus 1 is always positive. So the absolute value is fine if you put it, but if you don't put it, it's totally okay as well. So this right here is our integral. Okay. So we have just spent the last week and a day going over all kinds of new techniques for integrating functions. There's no more. So every integral can be found using some combination of these different types of techniques. Perhaps you start by doing some U-substitution, and then you realize, wow, after I do U-substitution, it looks like a partial fraction decomposition. So you try that, right? Or maybe you try integration by parts, and when you do integration by parts, you realize that part of it turns into something where you could use trig substitution. So then you do that. So every single integral at this point that is able to be integrated will always be integrated by one of these 5 things: U-substitution, integration by parts, integrating powers of trig functions by doing identities and so on, trig substitution, or partial fraction decomposition. And that's it. Those are the only options, other than just the basic antiderivatives that we learned back in Calc 1. Okay. So I just wanted to show you one last little trick, which is a shortcut to find A, B, and C sometimes. So I've gone ahead and started this process down here. But if we were to break these apart, notice that the easiest way to do each of these is to split them up into individual parts. Now, some of you may have tried your best to do some U-substitution with this problem right here by letting x squared plus 1 be u, and then trying to solve for du up here. The problem is you can't really do that, because if there's an x in the numerator, you would integrate that much different than if there was a constant in the numerator. Okay, so the first thing to do here is with irreducible quadratics, you will typically always break this up into 2 separate integrals. Okay, one integral that would have an x in the numerator, one integral that would just have your constant. We're now just multiplying the left side by x times x minus 2 times x plus 1, which will cancel the denominator there. And we're doing the same thing over on the left side. We're going to cancel out each of the denominators. So we have to multiply by each of the denominators. So notice that each one of these factors individually, the x, x minus 2, and x plus 1, are going to cancel when we multiply. And this right here is what we have. How do I solve for A, B, and C at this point? Okay, what have we been doing today in order to solve for A, B, and C?
Grouping the like terms.
Yeah, grouping the like terms from the right side with the like terms on the left. But before we can do that, we have to distribute all of this over here, distribute all of this over here, distribute all of this right here, group together the x squared terms, group together the x terms, group together the constants. And then we would equate the constants on the one side to the coefficients on the left, which can sometimes be a challenge, and sometimes it's just a tedious process of solving a system of equations. But this system of equations right here would be a 3-variable system of equations if we were to do this method. I'm going to show you now a little shortcut. The shortcut basically allows us to automatically solve for the individual values. And you could do this shortcut if the denominators are distinct factors like this. You could do this shortcut if they're repeated factors. You could do the shortcut if it's irreducible quadratics. But it turns out that this shortcut works best when they're all distinct factors in the denominator, when all of these factors are different. So the way this works is that you're really just going to say, what would cause each of these factors to become 0? Well, I could see here that x minus 2 would be 0 if I plugged in x equals 2. And x plus 1 would be 0 if I plugged in negative 1. And x would be 0 if we plugged in x equals 0. So that's exactly what we're going to do. We're actually just going to, in this case, we're going to say, let's just let x here equal 0. We got a question down here. So if we let x equal 0, then let's just look at what ends up happening here. I'm going to replace the entire equation with 0. But if we do that, notice that this becomes 3 times 0 plus 2 is equal to a times, well, 0 minus 2 is negative 2. And then 0 plus 1 is just 1. Plus b times 0 times 0 plus 1, which is 1. Plus c times 0 plus 0 minus 2 is negative 2. But look at what's awesome about this. By letting x equal 0, it's going to cancel out the terms that have a factor of x. So without really doing much work at all, I know that these two terms right here and right here are automatically going to cancel when I plug in 0. Likewise, this term and this term will cancel when I plug in negative 1. Likewise, this term and this term will cancel when I plug in x equals 2. So notice that all we're doing now is plugging in certain values that are going to cancel all of these terms. So all that's left on the left side here is 2, and all that's left on the right side is negative 2a. And look at how in one step, we find out that a equals negative 1. Cool. So what should we try next?
X equals 2.
Sure, so let's let x equal 2. And look at how nice this is. When I let x equal 2, I now plug in 2. 3 times 2 plus 2. But notice that it's going to cancel this term and it's going to cancel this term, so I'm not even going to bother writing them. So all that's left on the left side is b times 2 times 2 plus 1, which is 3. This gives me 8. 6 plus 2 is 8. Equals 6b, which tells me that b is equal to 8/6 or 4/3. And I found the second one. So you can see that with this method, you don't need to set up a system of equations. You don't need to equate coefficients. This is just a shortcut that is helpful to find a, b, and c. Because we don't want to waste all of our time finding a, b, and c when the whole point of the problem is to integrate. So we're going to do one last example, or one last substitution. And we're going to say, let's let x equal negative 1. So that gives me 3 times negative 1 plus 2 is equal to, but again, if I plug in negative 1, this term cancels and this term cancels, because those are both going to go to 0. So I don't have to worry about that one. So all I'm left with is the term that involves c. So c times negative 1 times negative 1 minus 2 is negative 3. So that means that we're left with negative 3 plus 2 is negative 1. And on the right side, we're left with 3c. You've got a single simple equation with only c's, which tells me that c equals negative 1/3. I don't mind what method you use in order to find your a, b, and c. These are not even the only methods. I mean, there's other ways to find a, b, and c as well. You could find a, b, and c by taking derivatives of this original green equation. There's cool little tricks about how to solve for A, B, and C, but the point of this is just you could do this with only A's and B's. You could do it with repeated linear factors. You could do it with anything.